Well, it's certainly a great pleasure to be here. Thank you all for listening. And so what I'm going to talk about today and also on Friday follows roughly the same spirit as my talk yesterday. So basically, I guess the key difference is I won't be rushing to cover so much ground in half an hour. So hopefully I'll be able to explain in detail some of the more exciting problems and interesting solutions. And also at the same time, because we have more time, in case, and as Dima mentioned, because we all have different backgrounds. So if you have any questions about the notation and some of the results I'm presenting, please feel free to stop me and asking questions. So again, like I mentioned yesterday, I think when we use tensor methods for any data analysis, of course, it brings a lot of power, but also at the same time, it presents many new challenges. So what I will focus on today is in discussing in further details how we can take advantage of this new power, while at the same time to address various fundamental challenges. Roughly in comparison, I showed you yesterday as well, roughly in comparison analogy to this so-called professor's cube. And so basically the type of challenges I want to focus on, as I highlight here, one is probably more conceptual, the other one is more computational. So the conceptual challenges including, say, what types of rank and eigenvalue or signal value decompositions would be useful depending on the context, depending on the scenario. And this is akin to, for example, playing the two-dimensional puzzle, and then we're interested in playing three-dimensional puzzle. They're both puzzles, but of course they require different skills. Same thing here, we're very familiar with how to deal with the matrices, but moving to higher order tensors, it requires new thinking. And as I will discuss in further details, also require a little bit of further care as well. And the other aspect is more from the computational side, which is akin to the comparison of playing Rubik's Cube to the more sophisticated so-called, to scale it up to the so-called professor's cube. So for those who have played the Rubik's Cube, probably can solve it in a matter of minutes. But last time when I was preparing these slides, I checked the world record for professor's cube with a 17 by 17 by 17 cube, and took somebody the world record a little bit over 8 hours to solve it. It's not so much about his thinking about how to do it, how to do the next move and so on and so forth, but rather just a sheer number of operations require that much time. This is essentially the same issue we have when dealing with today's data analysis problems, because we usually have large scale data sets and the number of basic operations required is going to increase exponentially as the dimension increases. So we need to be mindful of the computational challenge. So what I will do is today is to use several examples, again, some of the very basic ones to illustrate some of these challenges and how we can navigate through these challenges. From, sorry, actually, somehow, yeah, this is probably. Yep. So from a data analysis perspective, I shall focus on two main aspects from a statistical point of view. Basically, the effects of randomness and the effect of high dimensionality. The effect of randomness goes in the following way. Of course, tensors have been widely used in different areas. I'm a statistician, so when I look at a word, I think about uncertainty, I think about randomness. So what I will be focusing on is what are the effects of randomness, or more precisely, uncertainty propagates through your modeling, and affects your modeling, affect you how you estimate the parameters and make valid inferences. And another aspect is high dimensionality here. Actually, I need to be a little bit more precise, because when it comes to tensors, there are multiple ways you can characterize dimensionality. One common way is, for example, in quantum physics, the dimensionality oftentimes is referred to essentially the number of modes. So when the order of the tensor, and usually you have very high order of tensor, but the dimension on each mode is relatively small. And when it comes to data analysis, well, usual machine learning or statistical data analysis, we actually have a slightly different, we have a sort of a different angle. Basically, the mode typically is not that high. Like for example, thinking about the computer vision, the mode of the tensor usually is 3 or 4, depending on you have a 2-dimensional image or 3-dimensional image. So the mode is relatively small, but the dimension of each, well, the order is very small, but the dimension of each mode is much higher. And that's my focus here in the lectures. So what I will be focusing on essentially for most of my talk, just to fix ideas, I'll focus on just a third order tensors. Of course, I'll talk briefly about how to extend to higher order tensors, but nonetheless, the order of the tensor, I always view them as sort of small. But nonetheless, what I will deem as high dimensionality is essentially the dimension of each of the mode actually is very, very large. And many of the discussion centers around how to deal with this sort of large, this high dimension along each mode, and how the behavior and the problem would change. So I structured my discussion, actually today's talk and Friday's talk, in the following way, essentially roughly along the lines of this sort of classical way of viewing machine learning. One is supervised learning, the other one is unsupervised. The difference being in supervised learning, our goal is more on the prediction. So you look at your current data sets, you want to know in the future, if a new instance comes in, can you say anything about the potential outcome? The unsupervised learning is more like classically in statistics we call exploratory data analysis. I'm presented with a data set and I want to extract its main feature, be it a dimension reduction, be it a clustering. So I roughly structured my talks along the lines of these two different subjects. And today I'll focus primarily on unsupervised learning. And on Friday, I'll move on to more of the supervised learning side. Again, just like what I did yesterday, I'll focus on three complementary aspects of data analysis, namely modeling, inference, and computation. So let's start with the modeling. Just to be a little bit more concrete, let me start with a data example. And this is actually a data example originated from a collaborative project in analyzing, this I know is a little bit fancy term, but basically I have a spatial temporal gene expression data from the human brain. And the idea is as follows. So actually this data was collected in the tri-state area. So basically New York, New Jersey, and Connecticut. And it's done in the Yale Medical School. This is actually one of the benchmark data sets in doing this sort of so-called transcriptome in the brain. So essentially the idea is as follows. So we take these subjects and we measure the gene expression at different brain regions. And of course, these subjects are of a different age group. And the idea basically is as follows. When I take this gene expression, of course, I'm measuring, in this particular case, about 20,000 different genes and about 15 different age range, and also about 16 different regions in the brain. So naturally, you can think about organizing this data in the form of a third order multilinear array, when one index representing gene, one index representing the region in the brain, and one index representing the age group. And of interest as a first step in any data analysis, of course, what we want to do is to do a little bit of signal denoising and reducing the dimensionality. And naturally, if you think about the classical way of doing this, is principal component analysis. And usually in statistics, we're interested in formulating data as a matrix. Naturally, we do singular value decomposition. Now, because we have these sort of three different indices, naturally, you want to ask if I can do similar things. And of course, this enables interpretation as well, because the idea essentially is if I can represent this linear array as a sum of this sort of so-called elementary tensors, basically this sort of a tensor product of one-dimensional vectors. This allows us to interpret this as different interactions of spatial patterns and temporal patterns. So very natural idea. And this is what we set to do initially. And sorry, somehow I have to, moving slides is a little bit difficult. Okay, so basically the problem we have here is actually a very simple one. We want to do low rank approximation to a tensor. So let's call this sort of measurement of gene expression, this sort of gene, time, and space. So we have this third order multilinear array, let's call it X. What I'm interested in here is whether or not I can extract a signal. This signal can be represented as a sum of a small number of elementary tensors, basically this product of all these vectors. And whatever I cannot explain, let's just call it noise. So basically, these are the features that are more essential to data analysis. So basically from an algebraic point of view, what I'm looking for is very simple. If I'm presented with a tensor, can I find its best low rank approximation? Well, of course, this is a problem has been around for a long time. And there are many, many algorithms and solutions presented in the literature. This is a very incomplete list, but the bottom line is the following. One, this is not as a trivial problem as in the matrix case, where we can just simply do single value decomposition. Two, the good thing is there are many algorithms that have been developed and there are many softwares out there. So from data analysis point of view, you can just dump the data into this software and then get these results. The question, of course, is what are you really getting from these softwares? And most often, actually, at least for this data set, we did try quite a few different software. And the main annoying thing is they all give different results. Of course, just as so often in practice, you look at each of these results, you can probably see some of the story, some of the commonality among them. But nonetheless, there are also very, very significant differences between these results. So how do I make sense of that? And perhaps a little bit more, even a little bit more fundamental and a little bit more puzzling is if you think about this sort of low rank approximation problem, as I mentioned earlier, we know these problems is ill-posed for a non-trivial subset of all these tensors. So this means from data analysis point of view, even if you can get a result from the software, how do you know really you are getting the best low rank approximation, not just a sort of you stop an algorithm somewhere, has nothing to do with the best low rank approximation. And also, we know in general doing the low rank approximation is NP hard. So any of these software, they actually, my experience is they usually stop very quickly. And how do you know, even if the problem is not ill-posed, how do you know that your algorithm, your software did not stop prematurely? And in practice, these kind of questions obviously is puzzling and is annoying. And this may also contribute to the fact that different algorithms may yield different results. So of course, from data analysis point of view, this is highly unsatisfactory because we need some sort of guarantee, or at least not the exact certificate of whether to certify whether or not you get the global optimum, but nonetheless, we need some guarantee that what you get from your data spilled out from your software is reasonable. And actually you can say something about its performance. So this actually brought us back to square one, to really thinking about what we are doing and how we can really do this sort of principal component analysis for tensors in a sort of more principled way. And the center to all of this, we want to answer several very basic questions. The first question is, really, is it worthwhile? Because after all, to do dimension reduction, there are many things we could do. And the simplest thing would be just not to think particularly tempting for this particular data set, because you have tens of thousands of genes, but you don't have that many time points or spatial locations. Why don't you just collapse this into a matrix? Then you can forget about all these sort of issues, challenges related to a tensor. It's really worthwhile to think about organizing data in the form of a multilinear array and thinking in terms of tensor. The second question is more as a statistician to ask, is it possible to extract the signal? And this is very much related to the modeling issue. You can have a wonderful model, but nonetheless, what you can do in the model depends on how well you can infer the parameters from data. So whether or not it's possible to extract the signal to estimate all these features you want, or the principal components you want, this is also essential. And the last one, again, goes back to the computational issue. Is it really feasible? Is it computationally possible at all? And again, I just want to emphasize, my focus here is on high dimensional problems. Again, by high dimension, I mean the dimension of each mode is very, very large. And here to fix ideas, of course, in this particular case, is not the case for my data, but nonetheless, just to fix ideas, I'll just focus on a cubic tensor, third order cubic tensor, which each mode has dimension d. So again, I'll just refer to d as a dimension of the tensor since we're fixing the order of the tensor at 3. So this is basically the setup of the problem. And
so Ming, can I ask a question?
Sure, go ahead.
You mentioned that you started with a tensor that is genes by time, by space, and that you're hoping to, when you do a candidate decomposition or a canonical decomposition, you are hoping to get a signal.
Yes.
Do you expect to have more than one signal, or are you trying to separate the signal from the noise?
Well, there are two goals here. The main goal, actually one of the simplest goal, would be to do dimension reduction, because the data, all these gene expression data are highly noisy. So you want to do denoising. And of course, when we say denoising, this is actually it's a lot of precise goal. So mathematically, what you try to do is I want to do dimension reduction. Basically, I want to find a small number of rank 1 tensors to represent it. And the rest, I'll just put them into the category of noise. Not because they are exactly stochastic noise, but nonetheless, the low rank part is the part we feel like carries most signal. And of course, the reason for doing this is exactly what I want to talk about here in this slide. Is when this rank 1 decomposition, we have the possibility to interpret all these rank 1 components as an interaction of, say, for example, if I take the first one, this may tell you the dominating spatial pattern on how the brain grows, because we have different age groups over time. And then I would have a spatial pattern, and at any given time point, what's the spatial expression of a particular gene? And then I have an interaction between the two and how that is spread out over different genes. So in a way, this is a model which allows us to do dimension reduction, allows us to reduce the effect of noise, and then at the same time offers some potential explanation. And of course, just like all the explanatory data analysis, this is not a precise data generating model. So that doesn't really tell you how brain functions, but nonetheless, this is a good way, sort of a collaborative way to support other theories already there in terms of brain development. Does that make sense?
Yep, thank you. So you're hoping that each rank 1, it represents different groups of people. So people over 60s, people in their 40s versus people in their 20s. Is that kind of the idea behind it?
Similar, but not exactly the same. So basically, I want not different age group, but rather say how the brain, well, let's just say how different regions develops over time.
Okay.
Yeah.
Got it. Okay.
Yeah, thanks. Any other questions?
Yeah, is there an emphasis on the type of SVD that the type of decomposition that you're using? I mean, I do understand that there is the CP decomposition, and you also have the talker.
Yes.
And there's also a recent one that uses that does more like matrix XV, like decomposition that uses decomposes a tensor into uses some type of a Fourier transform. I think it was by Kilmer. So I'm just trying to understand the type of tensor SVD that you referred to.
Well, that's a very good question. Actually, I should have made this clear. Well, obviously, when it comes to tensor, there are many different ways you can decompose a tensor. And here I'm just using CP decomposition. Well, there are a couple of reasons I use CP decomposition as an example. One is just like what I said earlier. CP decomposition actually offers some explanation. In a way, this sort of, you can interpret this as different interactions. And this also relates to what I discussed yesterday as well. So in many ways, you could also think about this as factors. So in a way, CP decomposition naturally has this explanation. Of course, having said this, other decomposition you could make sense of other type of decompositions as well. Most notably, for example, Tucker decomposition. People have also used Tucker decomposition as a way of doing dimension reduction in analyzing high dimensional data. And there are many commonalities in terms of challenges between using different decompositions, but there are also significant differences. Here, of course, I focus primarily on CP decomposition because I will come back to this issue probably a little bit more, mostly because Mostly because we want to, in a way, to sort of be consistent with this sort of factor interpretation. And oftentimes, particularly when it comes to machine learning applications of these sort of tensor methods, we often talk about latent factor models. And the CP decomposition just arrives very naturally compared with other type of decompositions.
Ming, there's one more question that is coming from Jiro.
Yeah, thanks. So Ming, I was wondering, are you going to give us a more detailed comparison at some point of standard stuff like PCA and tensor decompositions? Because in PCA, the individual modes they don't need to be low rank. So they could correlate the three variables, let's say gene, time and space in a more complicated way. So are you going to give us some comparison?
Yes, well, yes and no. I'm not going to give you a numerical comparison here, but I will explain why, which is exactly what this slide is for. Because essentially what I want to argue is if you do PCA and you won't be able to, well, I'm sort of repeating myself a little bit. So you won't have this interpretation of the spatial temporal interaction, but nonetheless, you will have sort of a factor, the principal component in a way representing the joint effect of the spatial and temporal pattern. So in this particular case, what we realize is if you do this sort of tensor decomposition, as I will show a little bit later, I won't show the result for the classical PCA, but I will demonstrate what you can get by using tensor PCA, for example, using in this particular data set. What are the new things you could get out from it?
One more question, Jose. You're next. Jose Landsberg, are you still?
Okay. In terms of this brain tensor, what's the interpretation of R, the rank?
The rank actually has no, well, in a way, the rank doesn't have much interpretation. It's more like in principal component. This is the dimension you can reduce. Well, you would think the signal could be approximated by. So usually you want this dimension to be relatively small, just like in principal component analysis. And this is a key point. Actually, from more of a mathematical point of view, this is a very key issue. From a statistical point of view, this is also a very important issue, mostly from practical point of view. How do I choose this rank? And oftentimes, actually, I should say, at this point, there's no universally good way of choosing this rank, even for principal component analysis. There are a lot of tools we could use. One of the most powerful one probably is the so-called scree plot. And later on, I will show how we can extend this concept to the tensor SVD case. So in a way, I think in short, this is sort of more in practice, what we do is we choose this R in a more heuristic fashion.
Yeah, but even if you're choosing in a heuristic fashion, you must have some something in mind you want to measure that.
Yes, yep. So that basically is the signal to noise ratio. Sorry for interrupting. So basically what we are looking for is signal to noise ratio. So how much variation you could explain, because if you think about, let me go back here. So if you think about X, you can look at the variation among all the entries of this tensor. And then you look at the variation that's explained by the signal. And obviously, when you increase the rank, the more percentage of variation you can explain by the signal. But your hope is you want all these rank 1 tensors, each one of them, to be able to explain as much variation as possible. Let's say you have a rank 100 approximation explains 99% of the variation, versus you have a rank 3, which explains 50%. Then the latter one probably is more useful than the former one, because it's a very low rank one. It explains 50%, so in a way it captures some of the essential features of the data.
I'm surprised to hear you say this. I always thought that the CP decomposition wanted to capture every one of those rank 1 tensors are supposed to be capturing approximately the same amount of information, rather than from most to least, unless you were to sort of do it the way you do it with matrix SVD, where you compute the top rank one, subtract it, and then the next one and the next one. With a CP decomposition, it was supposed to be kind of equal in amount of information, each one of them. Am I incorrect? Are you using a variant of the CP decomposition?
No, actually, I think it depends on the context. At least from my perspective, I think this is in parallel to the classical PCA, because.
So you are doing like computing the first rank one, subtracting it, and then the next one and the next one. Are you doing a greedy version?
You don't necessarily want to do that. You could do just to say, I find the best low rank approximation. So there is an issue here, which probably as you alluded to, because if you have a best rank 2 approximation, you have best rank 3 approximation, the best rank 2 may not be a subset of the best rank 3. So this is different from the usual classical PCA. But nonetheless, even if your fate, say, for example, best rank 3, and they would have different, basically, if you look at their norms, basically, or in other words, you think about how much variation they would induce, they will have very different magnitude. So this allows you to sort them in a way like how much variation each of the elementary tensors would explain. And in general, they wouldn't be comparable. And in most of the examples I've seen, in practical examples I've seen, they will have vastly different contribution, when the first few leading ones contributing most, and the later ones contributing much less. Does that make sense?
Yeah, I'm sorry. Okay. So go on, please.
Okay, I think we are here. So first of all, I just want to emphasize, in many ways, the idea of doing tensor SVD and the classical PCA, if you don't look beyond the noise, you just look at the signal, there's not much difference. Because if you say, for example, the signal indeed is of low rank, you can always matricize it. When you matricize it, if you have it, well, of course, these 2 ranks, of course, I need to be a little bit more careful. They are not exactly the same. But in general, what you would have is, suppose you have a tensor T, the signal, which is of low CP rank. Then when you decompose it, when you matricize it, it's still going to be of low rank. This is what we would be mostly interested in here, because we want to do dimension reduction. So in a way, these 2 methods are closely connected. So what are the key differences here? The key difference, as I emphasized, is this idea of identifiability. And if I'm able to identify each of these components, what this allows us to do is to think about potential interpretation. And later on, of course, this typically is sort of a more upstream analysis. When you do data analysis, after you do this sort of a PCA stuff, there will always be downstream analysis, for example, in doing clustering, when even doing prediction. So basically, the idea here is, if I'm going to use CP decomposition, what this allows me to do is to interpret these as different interactions, and then allows me to have more confidence in the downstream analysis. So this is the main advantage, in a way, from conceptual point of view, from statistical point of view, why we are more interested in using tensor SVD rather than just the classical matrix SVD. But of course, as I already alluded to yesterday, this actually comes from a heavy cost. Actually, in many ways, this almost looks like fool's gold. The reason is very simple. Whatever modeling you have, you just model the signal, just as in statistics, or in data analysis, usually this is what we do. We can make assumptions about the signal, because these are the things we are looking for in the data. But nonetheless, what you observe is not the signal. It's a signal plus noise. And the question here is the following. Suppose, or in a very simplest case, suppose T is your true tensor, the true signal, which is low rank. And what you observe is just this true signal plus noise. Let's even make it simple. Let's say the noise are just the IID standard normal. How do I go ahead and estimate this true tensor? This is basically what we have here, right? If you think about this T, this is the signal part, this is noise, this is what I observe. And then what I will go ahead to do, forget about how we do it. Forget about the algorithmic parts and how we do the computation. I just ask a very simple question. How do I infer this signal from X? Well, in statistics, if you know a little bit about statistics or data analysis, the most natural thing to do would be to do the so-called maximum likelihood estimate, which in this case, because we're using Gaussian, we're assuming the noise are Gaussian. Basically, this is the best low rank approximation. Suppose I even tell you, for example, this signal just has rank 2, just like what Alex and I discussed earlier. Suppose I know the rank is 2. Now what's the MLE? I'm trying to find a rank 2 tensor A so that I minimize the squared Frobenius norm between the difference between the two. The issue is here. We know as long as I is greater than 1, this could be U-opposed, meaning that this MLE may not exist. And of course, you can, at least in a sort of a more heuristic way, you probably will think, well, the signal I look for maybe is more regular, because the U-opposedness happens, say, for example, when this tensor, when X actually has particular particular features. Suppose, say, for example, this X is fairly regular. There's the hope that the MLE is always well defined. But the issue here is I can make such assumptions about the signal. I cannot make such assumptions about the observation. The observation is always a signal plus noise. So what happens is the MLE may not exist. And this, of course, is a very simple example, and it's a very well-known example and a well-known phenomenon. The issue here is whether or not this is indeed what we would call pathological, meaning that this will only happen in very rare cases. Suppose we are able to make assumptions, we are willing to make assumptions about the signal. Is it possible we can overcome this? Turns out you can't. This actually has nothing to do in high dimensionality or not. We can look at an even very simple problem. Suppose your true signal is, let's just focus on tensors that are 2 by 2 by 2. Your true signal is as it showed by this figure here. You have 1 here and 1 here. Obviously, this is very nice tensor, this signal. But if you just add Gaussian noise to it, the probability that your best low rank approximation does not exist is always non-negative, it's always positive. What does this mean? Well, you may be lucky for a given data set. You can compute the MLE and the MLE indeed exists. But as a method, if you run this method on different data sets, then there is always a possibility that your MLE may not exist. Of course, your software may not tell you, but this is just the hard truth that sometimes you are going to get it wrong because the MLE just doesn't exist. And this is an issue of signal to noise ratio, but no matter how strong your signal to noise ratio is, as long as your signal is finite, you will always have this issue that this probability is non-zero. And so let me just rephrase this again. Basically, this highlights what happens if you have a noise in the data. You have a very well-behaved signal. You add a Gaussian noise to it. Now, all of a sudden, you won't be able to compute the MLE. So you won't be able to recover the low-rank tensor. And this, of course, has a very significant impact. This basically tells you in many ways, you are really looking at a fool's gold. All is identifiability, all is interpretability, because all you are doing is you are just modeling the signal. With noise, this just becomes elusive. Any questions? Okay. So,
sorry. Can I ask a silly question? So just to understand, sure, for outsiders like me. Mm-hmm. So the Frobenius norm is one where you take, so if you take a basis for your vector spaces, mm-hmm, and you write the elementary tensors, so you take one tensor from one basis set, tensor another, mm-hmm, thing, etc., etc., etc. Mm-hmm. There will be an orthonormal basis for all of your tensor sets, right? So in other words, it's like the sum of the squares of the entries of your tensor.
Yes, these are the sum of squares of your entries of tensor. Yes, exactly.
And can you say a little bit, even for matrices, there are so many nice norms that you can use, but for tensors even more. Why is it so nice to use the Frobenius norm?
Oh, that's a very good question, actually. In this case, it's very natural because maybe I should explain a little bit. This is what we would call maximum likelihood estimate. So the basic idea is the follows. Because I'm assuming the errors are Gaussian, are standard normal. So what you can do, basically, if you look at the ijk entry of X, it's going to be a normal random variable with a mean Tijk and a variance 1. And all of them are independent. So we'll write down the joint density function of it. And you realize the joint density is going to be proportional to exponential of the squared Frobenius norm of these two. So naturally, I want to maximize the likelihood. This is a very, very simple idea, a very common idea in statistics or in data analysis in general. So this leads to the squared Frobenius norm. But you are exactly to the point, as later on I will demonstrate. Indeed, oftentimes using other norms, even if there is some deficiency in other norms when it comes to this problem, and it yields actually much better estimate.
Thanks very much.
Sure. Any other questions?
Sorry, I have a question.
Yes, go ahead.
So you have an R in the MLE problem. So is this R fixed beforehand, or like how does it?
Yes, this is basically how the order of the rank. Well, basically the number of elementary tensors you want in your signal, and this is usually fixed pre-hand. But having said this, in practice, just sort of as I think JM asked this question earlier, in practice, we do need to choose this R heuristically. So that means this is typically done in a trial and error case. You try different R's and then you figure out which one fits your data better.
We have a question over here. Oh, sorry. So we have a question in the chat. Are you computing orthonormal rank 1 tensors, or are you using the standard CP decomposition?
For now, I'm using standard CP decomposition.
So is there any reason to believe that those rank 1 tensors are orthonormal?
They are actually. This is exactly what I will do in the next slide. I want to argue, you want to impose not just orthogonality. There are other type of conditions you could impose, but nonetheless, you do want to do some of that. Let me just rephrase a little bit. So far, I haven't made any assumption about how the CP decomposition, how these sort of these elementary tensors, what kind of actual condition they need to satisfy. I'm just taking a generic CP decomposition.
So the generic version, does it have any orthonormality constraints on them?
No, it doesn't.
Okay.
So it's kind of like, this is basically, think about in a very naive data analysis point of view. I have this data. I just want to do this sort of approximation using elementary tensors. I haven't imposed any conditions on this. And this is actually, in a way, sort of very unfortunately, commonly done in a lot of, in the literature and in a lot of sort of practical situations. But what I do want to argue, maybe in just a couple of slides, is you don't want to do that precisely because of this behavior. One, because of the unestimability. And later on, next slides, I'm going to talk about, it also has implication when it comes to estimation, because this is very unstable if you don't impose any assumption to it. So suppose, well, any other questions? If not, I'm going to go on to the next slide. So basically, I'm talking about the first problem I talked about is basically what you will have is no matter how you do the modeling, you need to always be mindful of whether or not you can extract the signal from it. Because the statistical modeling part, well, maybe let me step back a little bit because probably many of you guys don't have much statistical background. So the modeling part, in statistics, we refer to basically two main ingredients. One is the population. This is the stuff I'm interested in. This is a population model. Basically, it's done by probabilistic modeling. And let's just say we want to know exactly how many people got, let's just say COVID-19. If you know everybody, the status of everybody, of course you have the answer. But since I don't want to ask every single person, I need to do a sampling. So in statistics, we have a population and we have a sample. And when you do modeling, you are modeling the population. And then you do sample. And of course, when sample, you always get a noise. The noise actually, I use this in a loose way because the sample is only one aspect of your population. And then you want to make an inference using your sample. So what's the difference here? The modeling part is you can do all kinds of modeling on the population side. This depends on your understanding about the problem. And then you do sample. And then, of course, when you do sample, there is always uncertainty depending on how you collect data from your population. And when you make inference about the population using your sample, now, of course, you need to be mindful of uncertainty and the role of noise, as I mentioned earlier, or the role of randomness. So what I'm saying here in this particular slides and the last one is the following. You can make all kinds of nice assumptions about your population model, just simply because you don't observe the population and you have to take a sample. Then these nice properties will immediately be lost. And one of these properties is suppose your population indeed is low rank in this sort of CP rank sense. And when you collect the data, you won't be able to go back and estimate it. So this is the unestimability issue. Now you probably ask, well, let's just say we're reasonably lucky. I have very high signal to noise ratio, which means I can compute the MLE with a high probability. Well, the MLE does exist with high probability. Then we still need to deal with how much uncertainty I have in the estimate. And this is more of a perturbation analysis. Basically, imagine this is your signal T. And this T tilt, let's just say this is your estimate. Well, you can look at these two tensors. It's very easy to compare. This is actually a very, very silly example. Many of you probably can come up with better examples. So T is your true signal, T tilt is your estimate. In many ways, you look at this estimate, it's a very good estimate. But now if you think about it, if you try to offer explanation, as I emphasized a lot, that when you do this low rank decomposition, you want to be able to have interpretability. That means I should be able to recover these bases. These E1, E2, these are the canonical bases. So basically when the first entry being 1 or the others being 0, the second entry being 1 or the others being 0, and so on. So these two tensors in terms of spectral norm, they are very, 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 very close, depending on how small epsilon is. But if you look at their singular vectors, they are very different. So what does this mean? This means even with a little bit of error in your data, you may be able to estimate your signal overall, but you may not be able to enjoy this interpretability at all. So now I just want you guys to think a little bit more about it. As I argued from modeling perspective, this often happens when using tensor methods in data analysis. You think about all kinds of nice properties tensor methods brings about. And in this particular case, it's interpretability. You think about if you go back a little bit, if you know a little bit more about machine learning applications, or you sort of heard what I talked about yesterday, you think about latent factor models. What this tells you is the following. If you have latent factor models, you can model it very well. You won't be able to compute the estimate. And even if you can compute the estimate, you won't be able to recover the latent factors as claimed. So these are sort of some of the main challenges when using tensor SVD for data analysis. As I mentioned, very unfortunately, people use this a lot in practicing data analysis. But nonetheless, there are some huge, bigger questions surrounding how you use it. And what are the issues here? The main issue is as follows. So far, we haven't made any assumption about all these sort of all these components in the CP decomposition, which is sort of in agreement with what we typically would do in the classical PCA. Because when I say I give you a data matrix, I ask you to do PCA, you don't need to make any sort of additional assumption. We just run principal component analysis. You would think you can do the same when higher order tensors. But here I just want to highlight that's not always the case. Actually, if anything, that's almost never the case. And it's very important that you spend a little bit more time to study the problem. And oftentimes what can help, as I would argue here, is some extra features. For example, as we talked about yesterday, if you think about from probabilistic modeling point of view, you may have non-negativity of the decomposition. So these components, all these use, it should have long negative entries, or you could have orthogonality. And all these kind of assumptions, you have to take them into consideration when you do tensor SVD as a way to do dimension reduction. Because otherwise you would run into this issue of instability, and you would run into this issue of unestimability. Even if you impose these assumptions, they don't necessarily totally overcome the issue of unestimability, but nonetheless, this will be able to tie you together with a signal to noise ratio. And hopefully you do have strong enough signal. And if you don't, like in the case of exploratory data analysis case, that's why you always look for sort of also related to James' question earlier. You can always focus on the high signal part. If you do this sort of CP low rank approximation, only the leading ones, really you can reliably say, at least with some confidence to say, this indeed is a good estimate, reflects your model. And all these smaller ones, most likely they are artifacts of random noise.
Question?
Yes, Jen.
Is there any theorems that guarantee that these extra conditions are reasonable, or is this just ad hoc?
This is more ad hoc, actually, unfortunately. But there are some results, particularly when it comes to orthogonality, that's why I highlighted it. I'll talk a little bit about some of the results that would give us more assurance on imposing orthogonality, how that helps us resolve these issues. Okay, so I guess let's talk about this then. So suppose, well, okay, let me emphasize again. So as I
just want to make sure you heard me. You have 25 minutes left, so about a minute per slide.
Oh, okay. Okay, thanks. Okay. Well, this is going much slower than I expected, but nonetheless, I'll speed up a little bit.
But
So anyhow,
I mean, sorry to interrupt, but
sure.
Maybe we should not speed up and rather kind of make sure that we all learn. So
Okay.
I don't know, maybe Maria, maybe you can help us, and maybe there's something that we can do about the schedule or something like this, because there's a lot to absorb, at least for people like me who are outsiders. Sorry to be speaking up for the the bottom 50% of the audience like me, but
Sure.
I'm okay with it.
Well, I can reorganize the materials a little bit. Maybe I can, if we couldn't finish today, I'll defer some of the stuff to Friday. I do agree. I think it's better that we talk about less stuff in more detail than talk just like what I did yesterday, covering a lot of things, but not being able to explain things clearly. I agree with you. Yeah. Okay, we'll see how it goes. Yeah. Anyhow. So this is sort of more for modeling issue. So if you forget about all the details, I guess the message I want to deliver is the following. At least it's more of a cautionary message for those who do data analysis or statisticians in general. So just want tensor SVD is a good tool, but nonetheless, I think you got to be a little bit more careful. You need to work a little bit harder in terms of modeling. And all these benefits of interpretability, they don't come automatically. And you have to take into consideration of other particular structures. So from now on, actually, I talk about different conditions you can impose here. And from now on, I'm going to focus on a particular type of condition, which is to impose orthogonality among these elementary tensors in the CP decomposition. I see Adina has a question.
Yeah, I have a question. So these tensors, these rank 1 tensors that you had initially, is it safe to assume that they will be linearly independent over the vector space you're working with?
It depends on the context. It could, well, I haven't assumed I haven't imposed the condition they're linearly independent. But
the reason
obviously,
right.
Yes, go ahead.
Sorry.
Go ahead.
No, the only reason I ask is because, I mean, there are many Hilbert spaces you can impose, many inner products you can choose over your vector space. Is it clear why the inner product that we use for matrices is appropriate in this context? If they were already linearly independent, couldn't you come up with some new inner product with respect to which they were already orthogonal?
That's a very good question. In this context, for example, in this particular context, or oftentimes in other sort of data analysis, you want to just do dimension reduction. I think this is reasonable, just a classical Euclidean type of inner product is probably suitable. In a lot of ways, this has to do when assuming the noise is Gaussian or approximately Gaussian. But there are other contexts, indeed, by choosing different inner product could help the matter a little bit. And specifically, when it comes to, for example, long-term metric function estimation, which unfortunately I wasn't planning to talk about here, but nonetheless, this is a very simple one. This is sort of more like a discrete version of things. And in most of data analysis, most of data analysis problems I encountered, I think this is a reasonable way of doing things. But what you said, I totally agree with you. There are certainly contexts that could be helpful. Yeah. Okay. So if we move on from here, I'll move on to the next phase. So now suppose we do have this model, and we do have the signal which we assume to be of low rank. And I'm also willing to assume that all these principal components are indeed orthogonal of each other. Can we say anything about our ability to estimate it? And this essentially is an issue of perturbation, the effect of perturbation. Again, let's just look at this figure here. This is what we observe. X is a third order tensor. And then my signal is of low rank. And here I single out all these lambdas. Let's call these, because now I'm assuming all these sort of vectors are orthogonal. Let's call them singular vectors. So this is mode 1 singular vectors, mode 2 singular vectors, mode 3 ones. And these singular vectors are of length 1, so that I can write down these singular values, lambda 1 all the way to lambda r. So suppose this is my signal, very well behaved. And they are sorted, of course, in the order. Let's just say the singular values are long increasing. And then everything else is noise. And again, in statistics, of course, we often do is assuming the noise is Gaussian, IID Gaussian ensemble. Let's just make things even simpler. Basically, every single entry of this tensor E will have standard normal distribution. What are we interested in here? We're basically interested in how well, this from statistically speaking, how well can we estimate this use from X? So X is all we got to observe. Well, usually what this happens is the following. From the true signal, if it's orthogonally decomposable, then basically all these U's and the lambdas, they are uniquely defined. So let's just say these are my singular vectors. And from X, I want to derive an estimate. And here it's a little bit unclear how you derive these estimates. I will explain just in a little bit. But nonetheless, from a statistical point of view, let's just say, forget about computation for a moment. I should be able to derive these UK hats by having a hat on all of this. What this means basically is these U's when hat are functions of X. So this is basically a statistic. I can derive this estimate. And from a statistical point of view, the question I would ask is the following. How close are these UK hats to the UK, so as this figure illustrates? Is it possible I can match them up? Say, suppose the truth is U1, U2, U3, and my estimate is these dotted lines. Can you say anything about how well you can estimate it? Well, in general, this is a difficult problem. But since now we're assuming the signal is orthogonally decomposable, and the question is whether or not we can do something about it. Turns out indeed we can. Let's start with a even simpler one. Let's just say, suppose this is my true signal. Suppose from X, I can compute a T tilt. So this is again, something you could compute from X. But the reason I want to do T tilt is I'm going to say T tilt is also orthogonally decomposable. So these capital U's are just a collection of all these singular vectors along the first mode, and along the second mode, along the third mode, so on and so forth. And because I'm assuming the tensor is orthogonally decomposable, all these U's has also orthogonal columns. Similarly, suppose I can compute an orthogonal decomposable tensor T tilt from X, and this is what I would get. And the first question, let me first make things a little bit simpler. Suppose I have these two tensors, both are orthogonally decomposable. Can I say anything about the perturbation? Here, of course, we know in the case of matrix, this is very classical results. Let's first look at the case of singular values. If you look at the singular values, because both are orthogonally decomposable, you can just convert them into matrices, right? If you convert them into matrices, immediately you have, well, you can match up the singular values between both sides so that the difference, this is by Weyer's theorem, the difference is going to be upper bounded by the operator norm over the matrix-sized version of the difference. Of course, the matrix size, it doesn't matter your matrix size with which mode, because they are both orthogonally decomposable. So this will be maximized by either, if you do matrixization over either direction. Well, turns out you could say a little bit more about that. Instead of treating this as a matrices, you can treat this as tensors. In the case of tensors, what you can do is you can improve this from the spectral norm of the matrix-sized difference into just a tensor norm. And here I want to make, emphasize one thing here. This constant C1 is absolute constant in the sense that it doesn't depend on D. This is the issue I emphasized in the beginning. We're trying to deal with the case of high dimensional data analysis. So when D is large, and this is essential that this constant doesn't depend on D. And so if you compare the two differences, these two bounds, one is the spectral norm of the matrix-sized version, the other one is the spectral norm of the difference of the tensor. And of course, this is always smaller. And in general, if you compare the matrix-sized spectral norm and the tensor norm, they could be very different. And this, of course, you can always bound the ratio if you are allowed to use a constant depending on D. And that's what I want to emphasize here, because we want to get a constant that doesn't depend on the dimension D, because we want this to be applicable to high dimensional case. Even more, this actually is an issue actually will happen again and again. What we have here, this is general bound for any singular value. But if a singular value is large enough, then we can remove this constant. This will be 1. And here, I just one more note I want to add. If you compare this with the classical Weyer's theorem, actually, in the classical Weyer's theorem, you can just sort out these singular values. But here, in the tensor case, you don't want to do that. The reason is very simple. For singular values, it doesn't matter that much. But you want to match the singular vectors. So when two singular values are very close, sometimes you want to switch them. So basically, I want to add a permutation to the indices from your estimator. So suppose you have two orthogonally decomposable tensor. You should be able to bound the singular values in a very similar fashion as the matrices. And the only difference here is you don't need to do this sort of matrix-sized version, and you can just simply replace the matrix norm with the matrix operator norm on a tensor spectral norm. So these are singular values. Any questions here? Okay. Now let's look at the singular vectors. This actually is where most actions occur. Well, again, we can use the same strategy because both T and T tilt, for now, I'm assuming they're orthogonally decomposable. Then that means all these singular values can be categorized by basically matricize them. And if you matricize them, now all of a sudden I'm looking at the matrices. When you look at the matrices, this is the classical perturbation bounds by Davis, Kahan, and Wedding. And what this tells us is, sorry, actually there's a typo here, so this should be 3. So this is your true singular vector, and this is your estimated singular vector. And well, in this case, is the singular vector of T tilt. So you can, by Davis, Kahan, Welding theorem, you know the sign of this angle. Of course, you want this to be as small as possible. If they're the same, of course, this is 0. But nonetheless, the maximum of this is going to be upper bounded by 2 multiplied by, again, this is the matrix-sized spectral norm divided by the so-called eigengap. So what this means is this depends not only on lambda k, the k's largest singular value, but also how different is the k signal value to the k minus ones and the k plus ones. And this actually, for those who have experiences of doing sort of a data analysis for matrices, this actually is an annoying factor that we have to live with. in many different applications. So what's the implication? If you have two singular values very close to each other, just adding a little bit of noise to it, you won't be able to estimate any of the singular vectors because they will be messed up. Because the eigenvector, the eigengap here is too small. You won't be able to estimate the singular values, the singular vectors. Turns out this is no longer the case. Perhaps intuitively, perhaps makes a lot of sense. Like if we move to higher order tensors, this is no longer the case. Indeed, just like before, you can bound this essentially by, first of all, this is the tensor law, tensor spectral law, rather than the matrixized spectral law. Secondly, the denominator, instead of being the eigengap, now only depends on lambda k. And thirdly, actually for this constant, again, just like before, if the singular value, lambda k, is large enough, then you can reduce this constant to be arbitrarily close to 1. And this is not possible in the matrix case either. So in many ways, when you move from matrices to tensors, at least when we compare orthogonal decomposable tensors, the spectral decomposition allows us to compute a much better estimate of the singular values and the singular vectors. Yes, I see a question there.
Hi, so I guess my question is just, can you actually derive this from just Davis-Kahan theorem after projecting onto one of the eigenvectors? So you kind of did a matrix by projecting onto one of the vectors and then eigenvectors so that every other component becomes 0.
That's a very good question. Actually, you can't. The main reason has to do with, if you think about Davis-Kahan wedding type of theorem, you need to think a little bit on how this eigengap come into play. Because if you project into any one dimension, and what happens is, if you just look at from a matrixized point of view, then you won't be able to differentiate between projecting into this particular principle, or this particular singular vector, or the other one very close to it. So in a way, if you project to UK, it's hard to differentiate that from the projection into UK or UK plus 1 or UK minus 1, because the singular values are so close. So the the projection itself doesn't allow you to differentiate among them.
No, I wasn't thinking of projecting along a standard coordinate basis, but I meant you can use the orthogonal vectors in your decomposition as a basis and project along one of those directions, right? And then every other term will disappear, except for the term along which you're projecting.
I see your point. Maybe a better explanation is the following. You just think about an extreme case. Suppose you have one singular value has a multiplicity 2. Then in the matrix case, you cannot project. Yes, yeah, go ahead. That's good. Yeah. Yeah, Jianfeng, you have a question?
Yeah, so I guess I mean, it's kind of related with the question that I think someone asked yesterday. So I'm a bit confused about that. In the matrix case, it depends on the eigengap. But in the tensor case, I mean, we just see the eigenvalue there. So is there like a easy to explain intuition or insights why this is the case?
I
mean, this seems to say that it's more rigid, right? I mean, the tensor case. I mean,
exactly.
I guess due to orthogonality. So that both do not mix together. Is that, I mean, one way to understand this?
Yes. Yeah. So maybe let me do this in 3 steps. First of all, this is just as you alluded to, this certainly is related to identifiability, has to do with orthogonality. But this is different from orthogonality in the sense that you cannot derive similar result based on purely just let me step back a little bit. So I think the intuition behind this is exactly as you mentioned, orthogonality is much more rigid assumption here. Because of orthogonality, actually, don't forget one thing. So far, I'm assuming both T and T tilde are orthogonally decomposable. So in a way, this has to do in the local geometry, perhaps a little bit of the space of orthogonally decomposable tensors. It's much more rigid. They enter many ways you can perturb them. So this allows you to do this derivation. And from perhaps a little bit more sort of messy answer to your question, what this has to do essentially has to do with how the perturbation in each direction may affect the others. In the case of the matrices, because you have a perturbation in each of the direction, in the case of matrices, this actually accumulates much faster than in the tensor case. So this is essentially what comes into the proof for these results as well. Basically, you want to control how much the perturbation in each direction can affect the others. And it turns out, because in the tensor case, actually the impact is much more limited compared to the matrix case.
Yeah, thanks. So while you're on this page, actually, I have a previous question, short question. So for the C1 and the C2, are they absolute constants or they depend on certain parameters in the problem, like D or something like that?
No, these are absolute constants. Because, well, maybe I should emphasize this again. And the goal here is to have absolute constant, because when you deal in high dimensional problems, we don't want a D to come into play. And of course, this is also essential, because if this depends on D, this essentially is trivial, because you can always bound the ratio between the tensor spectral norm and the matricizer spectral norm.
Yeah, thanks.
Yeah, sure. Any other questions? How much time do I have? Maybe 10 minutes.
You have about 5 minutes officially.
Okay.
Officially,
Okay.
but I think people
Okay.
want to know more. Hold on a second. There's one more question from Enrique.
Yeah, hi. Yes.
Hi.
So my question is, so you are assuming that both T and T tilde are orthogonally decomposable, right? So
Yes, that's right.
this means, okay, so that means that their difference is also orthogonally decomposable, right?
No, they are not, but very close. These are difference between two orthogonally decomposable tensors. They are not necessarily orthogonally decomposable. That's the key. Yes.
Yeah. Okay. Because if you write the difference, apart from the trivial case where you have like identical rank 1 terms in both tensors that are going to cancel out, then you can write this difference also as a sum of
no, you can't.
Oh, okay,
in general,
okay,
you
yeah,
can't. Yeah.
Okay. Yeah. Okay. Sorry.
Because otherwise life would be easier. I agree.
Okay. Okay. Right. So I had another question, if I may. Yes.
Sure.
So this is more related to the application viewpoint. So from the point of view of applications, isn't this this assumption of orthogonal decomposition too strong? From the point of view of interpretation of the spatial and temporal patterns that you had in your example.
Indeed, it could be. Yeah. Again, I probably should emphasize. Oftentimes, it is a reasonable assumption. Actually, in many contexts, people have been imposing this assumption and getting useful results. But I agree with you. In general, this could be too restrictive. But on the other hand, as I have emphasized earlier, you have to assume some sort of assumptions to begin with, because otherwise, then you will run into the trouble of not being able to estimate anything or not being able to get a good estimate from anything. So I'm using this orthogonal decomposable as decomposability as an example that by adding additional assumption, you could get some good results. But nonetheless, there are other type of assumptions other type of conditions you could impose, like I mentioned, the non-negative constraints. So I'm just using, again, I agree with you. In many cases, this could be reasonable, but in some other cases, you probably want to think a little bit harder on what kind of conditions you want to impose on the principal components.
Okay, right, thanks.
Okay, so I guess maybe, well, let me try to finish this section and then probably I'll leave the computation to Friday. But nonetheless, so far there's still the result I presented is that probably still have very limited use because I'm just looking at the difference between two orthogonal decomposable tensors. And the problem I started with does not have this structure. So what I have is I have a signal. Let's just say we assume the signal is orthogonally decomposable, but I added a noise. I end up with X. and X is no longer orthogonally decomposable. But turns out this actually also goes back to Dima's question earlier, that we can't derive an estimate from X, but you may not want to just do the maximum likelihood estimate. You want to use other norms. This is based on the following observation. First of all, in light of the result I showed you earlier, if you take an arbitrary O-dicot approximation, orthogonally decomposable tensor approximation of X, if two approximations are both close to X, then the two of them are necessarily close. This is a simple consequence of triangle inequality. And now, using the results I showed you earlier, if two O-dicot tensors, they are close, then their singular values and singular vectors are also close. So what does this mean? I have this data set, which is a third-order tensor, and I assume the signal, underlying signals are orthogonally decomposable. This X is no longer orthogonally decomposable. I can ask for an orthogonally decomposable approximation to X. And in general, depending on which norm you use, and you may not end up in a unique orthogonally decomposable approximation. But it doesn't matter. If any of them, if you take two of them, they are both good approximation in terms of tensor spectral norm. And this is why tensor spectral norm plays a significant role, because if you look at the bound I showed you earlier, and you see tensor spectral norm is a good measure. So if you have two of them, two orthogonally decomposable tensors, both approximate X well in terms of tensor spectral norm, now obviously by triangle inequality, their difference is going to be relatively small, of course, up to a factor of 2. So if I define this T hat to be an arbitrary O-dicot approximation, best O-dicot approximation to X, then I can take its singular value, I can take its singular vectors as my estimate of the singular values and the singular vectors of T. And whatever I described earlier now can be applied. I can find the permutation of all these indices so that all the singular values are estimated. That can be upper bounded by, now I can replace this essentially by the spectral norm of this tensor, this error tensor. Similarly, for all the singular values, singular vectors, I can bound accordingly. And now, this is the spectral norm of the noise. So to deploy this in practice, what do I need to do? This becomes essentially a question more from probabilistic point of view. Suppose I have random tensor. If you can bound the spectral norm of this random tensor, then immediately this leads to an estimate of the singular values and the singular vectors, and you'll get a bound on how well you can estimate them. So I won't probably conclude today's talk with a couple of examples. The first one is just this tensor SVD problem. Suppose I have just a rank R orthogonally decomposable component as my signal, plus a noise, which is IID Gaussian ensemble, as I mentioned, standard Gaussian. You can do the computation, as I mentioned, for a Gaussian IID Gaussian ensemble, spectral norm is going to be over the order square root D. So just plug this in, you know I can estimate all these singular values at the order of square root D, estimate all these singular vectors at the rate of square root D divided by lambda J and 1, whichever is larger. And I use this subscript P to indicate that this holds true when high probability, basically when probability tending to 1 in high dimensional case. And this sign basically indicates it's up to a constant, absolute constant. So basically, what this tells us is the following. All of a sudden, just using what I showed you earlier, you can just directly apply them to see how well you can estimate singular values and singular vectors of the tensor SVD problem. And you can put these together to show how well you can estimate the signal in a sort of overall fashion. This would be the squared Frobenius norm, the sum of squares of all these entries. So this is a very simple example, and you can also talk about a more involved example. Here I'm using one more, maybe two more examples. One of these examples is commonly used, as I showed you yesterday, this is sort of a prototypical sort of a latent factor model. Suppose I have a latent factor, thinking about this as different topics of a different topic of a document. And you have multiple observations that are independent, conditional on this topic, let's say different words frequencies. So you have X1 to XP, let's just say you have 3 different measures. And these are multivariate, each of dimension D. Then basically, you can formulate this as a tensor problem in the sense that if I look at the third order moments, basically the cross moment x1, x2, x3, this will be a third order tensor. The moment tensor will be of third order tensor, and each one of them would depend on, each component would be the mean of each one of them. And the issue here obviously is, this is all from a modeling perspective. You never know the moment. You have to estimate the moment. Now suppose, sorry, actually there's another typo here. This should be smaller than or equal to n. Suppose I have n IID observations of this x1, x2, x3. And I can estimate this moment just simply by sample moments. This is a very simple and a very straightforward thing to do. And then now this becomes an issue of quantifying how close basically is the sample moment to the population moment. And with a little bit of calculation, well, with a lot of calculation, I should say. Actually, this is actually an interesting question from a probabilistic point of view, with a lot of active research about how well the sample moment estimate the population moment. But nonetheless, I guess the point is, you can derive how well you can estimate these means. And again, this is of order square root d over n. And this only happens, this is also an issue I mentioned yesterday, that the sample size is sufficiently large. And I just want to note, this could be improved with better estimates, which perhaps for those who are familiar with the statistics and probability, is a little bit surprising. Because usually when we talk about moment estimate, say suppose you want to estimate a population mean, you use sample mean. If you want to estimate a covariance matrix, you use sample covariance matrix. But it turns out, if you want to estimate a third order moment or a higher order moment, sample moment is, in a way, is sort of suboptimal. Because for smaller sample size, the sample moments actually behave much more poorly. And there are much better ways of estimating the sample moments. So I guess I'm running out of time. And I'll probably...
You have 5 more minutes. I don't see any hands raised, but officially you're supposed to finish at 9:15 and 10 minutes for questions. But people have been asking questions, so you could, have 5 more minutes if you wanted to continue.
Okay, then maybe let me conclude with this example then, because this will be the last few slides I have for the inference part. I'll talk about computation tomorrow on Friday. A third example is of similar flavor. This is what people often refer to as independent component analysis. And one of the typical examples is the so-called cocktail example, where different people are speaking, and what we observe is superposition of this combination of all these different sort of different voices. And we want to be able to separate them. So put it mathematically, your signal is S, let's say is a d-dimensional random vector. And you put in orthonormal matrices here, A here. Basically, you are just doing different linear combinations of these signals. So what you observe is X. And the question is whether you don't know A, of course you don't observe S. The question here is whether or not from X, you can estimate A. And how is this related to a latent factor model? In a way, essentially has to do in a moment. So you can compute the moment, the fourth order moment of X. Actually, in this case, the better way of doing this is to think about the cumulant. But nonetheless, without introducing too much notation, let's just say we're interested in a fourth order moment. That basically is the expectation of the fourth moment of this random vector X. And you realize, you look at the IJKL's entry of this fourth order moment, and they are once dominated by basically you do a little bit calculation by all these AKs, and this K4SK is the fourth, is basically the curtices of the fourth order moment, or the curtices of the case component of your signal. So again, this is a more like a cumulant type of concept, but nonetheless, for each of the signal, you can compute this quantity. This the so-called curtices has to do in the fourth order moment of the signal. And the difference here is you have entries like IIJJ, and what this corresponding to is taking the expectation of xi squared and sj squared. So, but nonetheless, the cumulative tensor is given as the difference between this one and the lone tensor M0. And you can compute this out, basically has this tensor decomposition, which can be written as a fourth order tensor. And when the curtices is the curtices of SK, is a singular value, and all these AKs is a singular vectors. Again, just like before, what I can do is I can turn this into a moment estimation problem. I can estimate M4 by its sample moment, and then I go ahead and compute the best Odeko approximation to it, from which then I can infer the singular values and the singular vectors. And using the result I presented earlier, then you can argue how well you can estimate the singular values. The singular values allow basically the estimate the courtesies of all these signals. And at the same time, you can estimate all these AKs. And of course, A is orthonormal matrix. If once you estimate all these AKs, you can put them back into estimate of A. One more thing I want to note is here I talk about 3 different examples, tensor SVD, and then the multi-view problem, latent factor model, and the ICA. I showed you some of the rates you could get using the perturbation result I discussed earlier. And what I want to emphasize is, from a statistical point of view, these are what all these rates agree with what we often refer to as a minimax optimal rate. So what does that mean? That basically means if we just make these assumptions we have, like these are orthogonal and all these noises are Gaussian distribution, then basically these are the rates, the best rates you can hope for. And there are low other estimates that could achieve faster rate of convergence. And again, when I say rate of convergence in high dimensional setting, you need to be a little bit more precise. Basically, we have sample size, we have dimensionality. So in a way, I'm thinking about a regime when both of them could be large, but nonetheless, all these sort of big OP and all these sort of rate of convergence essentially is up to a constant, independent of D and N. So with this, I think probably it's a good time to stop, and I'll leave the computational part to Friday.
Okay.